As we go through a survey course, welcome in. Sorry about that. As we go through a survey course, you need to understand where actual analytical chemists fit in the field of science. They question everything. So when it was discovered that two chemicals reacted, wow, that's pretty neat. Then they discovered that two chemicals reacted and the solution got cooler or the solution got warmer. Immediately, the chemist wants to find out why. This is the study of the heat projected exothermic versus heat absorbed, which is endothermic. Now, all of these things come together to form the basis for what we're going to cover today. Now, rate law, which is what this is called, is traditionally one of the more difficult topics to interject into a survey course of general chemistry. But I hope I'll be able to get across the basics of this without making it inordinately complex. Now, you need to brush up on your algebra, your trig, sine, cosine, tangent, cotangent functions for graphing. And I'll tell you why. To understand rate law, which is an analysis of temperature change in a time, you have to graph a reaction in real time. In other words, take a lot of readings of heat change in a system over a period of time. And you do this with a graphic analysis of it. So what we're going to speak about today is graphing production, the product of an actual graph. So let's start from the beginning. Again, at this stage of development, I assume that you can full screen the board. It's fairly clear and it's fairly accurate. Energy needed in chemical reactions follow a rate of chemical reaction at a given temperature. Written out, it is reaction per volume per time. So there's three quantitative particles, if you wish, or parts, if you wish more accurately. Reaction, which I've described many times, in a volume and over a time frame. This is called the law of mass action, which is one of the fundamental laws of chemistry and physics for that matter. Again, reaction dependent on the concentration of the solution is rarely a catalyst. So it's almost always dependent on the concentration of the components. Now, there are some reactions that require a catalyst, but they're singularly unimportant to a course like this. Rate expressed is a direct proportion with the concentration of the substance in the rate expression as the order of the reaction with respect to that substance. Now, there are multiple K expressions, if you want, that are used to be a basis for what we call rate law. The first one is the rate is equal to constant 1 times the concentration of A. We'll call it later on I'll actually use something for this. And this is called first order in A. The second one is rate is equal to constant 2 times the concentration of A times the concentration of B, which is said to be first order in A and first order in B. I didn't write first order for B, but you should write that down if you're taking notes on this. 3, rate equals to the K3 times the concentration of the A squared. Now, for those uninitiated and didn't follow earlier, that means 2 in front of the molecular structure of the substance itself. 2 moles, in other words. This is called second order in A. 4, rate is equal to K4, which is the concentration of A squared times the concentration of B. Second order in A, first order in B. And last but not least, rate equals K5, 0 order. Now, the first order half-life is independent of the initial concentration of A. Thus, you have AA equals the independent concentration times E to the minus KT. Now, you got to go back and review your natural logs and your logarithm functions to know what that means. You solve for K. In other words, you reorder this, solve this equation for K, and it's minus 2303 times the log. That's what the natural log is. Times the concentration of A over the initial concentration of A. And if it's 50% complete, that would be a half-life. Thus, the half-life time is equal to minus 2303 log of 1/2 over K. Now, you have to look that up in your log charts. There's a log book that's available, or you can punch it in your calculator and find the log of 1/2. It comes out to be 0.693 over K. Now, as you've seen, I've facetiously written what in the heck is K? And I'm going to go through that step by step. Try to follow it objectively if you can. Don't get mired in the weeds, because it actually, from a mathematical perspective, is not very difficult. First, 0 order relationship. K is equal to concentration of A divided by the concentration, the change in the concentration of A divided by the change in time. And the units for that would be moles per liter per second. B, minus the change of the concentration of A. Now, why do I put minus in there? Because in a graphic analysis, these are almost all going to be negative order, so it can be fit on a straight line function. And again, you got to go back and review your graphing. This is the change in A over the change in time is equal to KB, K concentration of A. Now, you reorder that and solve for K. You get K is equal to minus 1 over the concentration of A times the change in the concentration of A over the change in time. Or, if you're looking for units, it's 1 over moles per liter times moles per liter per second. Well, the moles per liter cancel out, and you're left with 1 over seconds. And you would say that is in the first order. C, relationship. 1 over the change of A times the change in time is equal to K times concentration of A squared. You rewrite this and solve it for K. By now you should see what we're doing. We're actually taking all of these up above and finding the actual units to be used for the answer to these. Okay, so K is 1 over A concentration of A squared times the change in A over the change in time. And in other words, it comes out to be, in this second order, you could use concentration of A and concentration of B, and you rewrite the doggone thing, and it comes out to be the same units for all of these. And you come up with 1 over moles per liter, moles being squared, times moles per liter over seconds, or moles per liter second. So all of these that I have up here have the same units. and that's moles per liter times seconds. The next one, negative change in A over change in T, notice it's the basis we start with each time, is equal to K times A cubed, or 3 moles of it. Rewritten for K, it's 1 over A, the change, the concentration of A cubed, times the change in the concentration of A over the change in time, or written as 1 over moles per liter quantity cubed times the moles per liter per second. Moles per liter will cancel out. One of them will cancel out. You're left with the 2. So it becomes liters squared over moles squared seconds. And the last one is, again, we start with our basis, negative concentration of, or change the concentration of A over the change in time is equal to K times the concentration to the half power. Rewritten, it's K is equal, this is the half-life thing. K is equal to minus 1 over the concentration A to the half power, or the square root for those of you that still remember your mathematics, times the change in concentration A over the change in time. Or if you wrote it out, it's 1 over mole per liter to the half power times moles per liter over seconds, or the square root of moles per liter per second. Now, how do you use this? This is a bunch of gobbledygook. Sounds like mathematical gobbledygook for you folks that don't remember your trig or geometry, or second year algebra, which will where a lot of this stuff is used. So I'm going to take an actual problem. Again, all of these two come out to be subtracted time functions. So we're going to say nitrogen dioxide goes to form, now this is broken down, in other words, to form nitrous oxide or nitrogen monoxide plus oxygen gas. The rate expression is going to be the change of A at time 2 minus the change, the concentration of A at time 1. In other words, the initial, the one we used to start everything, divided by the change in T, or T2 minus T1. And when you mathematically run through that, you get the change of the concentration A over the change of time. Now, the NO2 rate is the change in the concentration of NO2 divided by the change in time. You got to make it negative so it'll graph. Otherwise, it won't graph properly. And you take points from instantaneous rate by the tangent point or the slope of the tangent. So if you've ever graphed a tangent, you know that you can take particular points on the line, go out to the axis, and get a designated point. That's how graphs work. You should hopefully remember that. The slope is the change of y over the change of x. Change of y over the change of x is the slope. Or in this case, it's the change of the nitrogen dioxide over the change of time is equal to the rate. And the rate is minus, remember, in order for graphing, the change of nitrogen dioxide over the change in time. Now, thus, the rate of consumption of the nitrogen dioxide, consumption means it's broken down, is minus the change in the concentration of NO2 over the change in time. Goes to form, that's what that little arrow always means. The rate of production of the nitrogen monoxide is change of nitrogen monoxide over the change in time, plus 2 times the oxygen, written in this manner. And that's the way it's used functionally. I hope that's reasonably clear. Again, I suggest that you kind of go back and review your math for graphing and logarithmic functions and how to do a tangent line. If you do that, this is not that complicated. Now, this is one of the hardest topics in a survey course in general chemistry. Now, next section of this, I'm going to go through and take a fairly complicated 4-step problem and walk you all the way through all parts of it. Now, it'll be gobbledygook if you haven't gone back and reviewed this stuff. So I strongly suggest you go back and review it. Let's see if I can look at the problem over here. Yeah, actually, I do 2 problems, not just one. So it'll give you 2 problems, one that's fairly complicated and another one that's fairly easy like this one. So between now and the next time, make certain that you've gone back over this and reviewed your graphing and realize that you can use the X and Y axis with a tangent to give you a point in time because it's straight line function, straight line out to the axis and straight down gives you your position on each one of the axes. So give that a go and we'll go after it next time.